So a few things just to start off with. The first is the third problem set is actually up and running. It's on my own homework site now. That homework site, it's linked to my own class homepage, now there's a link new link for the homework site. If you don't see it, refresh the page because it could be cached, the old version. It's on one of my servers, Robbie 2. Isidore Robbie was a famous atomic physicist of the early 1920s-ish. And anyway, so I named my computers after a bunch of them. Anyway, so the homework is on that site now. It seems to be working for people. You should have gotten an email with a login and password information. If you get stuck, let me know. I've gotten far. Okay, it's due on Friday, incidentally. I made it later than Wednesday just because I hadn't gotten to the material as of last week, so I wanted to give you enough time to assimilate the material before answering it. And I haven't gotten too many. Haven't gotten any responses back of problems, which is unique. Yay! So hopefully you won't have problems, and it will do what it's supposed to do. It gives you feedback. You get one official attempt, but 2 attempts at each question, 2 tries at ethis question. Just you use their own terminology, and with feedback, and it should work better. And I can give extensions if there are problems. I mean, it's just all this inflexibility of Colab seems to be mostly gone. Any issues with problem set stuff or thoughts? Okay. Second thing, I was asked to talk a little bit about the transfers of these conserved quantities, momentum, energy, possibly angular momentum, just to make sure everybody's on board with this, because they influence a lot of the behavior of things in the world, and sort of being able to watch these conserved quantities move through the world gives you great insight into the mechanisms that make ordinary life happen. So the 3 conserved quantities I've introduced, which is maybe all that will come up this semester, are energy, momentum, and angular momentum. They're, as I've said many times, conserved quantities are very rare in nature. Another one that shows up is electric charge, for example. Mass, to an extent, is a conserved quantity, but it's a little more complicated. So about those conserved quantities, when you have them, you're stuck with them until you transfer them elsewhere. So if you have energy, you can't make it go away. Same with momentum, same with angular momentum. You can simultaneously have more than one. In fact, you always do have a certain amount of each one. You have a certain amount of energy, you have a certain amount of momentum, a certain amount of angular momentum, and all 3 of them independently are conserved quantities. They sort of are, I wouldn't say they're completely unrelated to each other, but they're independent, and you have to conserve all 3 of them. The way in which you receive them or transfer them is different, and I've named them all. They each involve a very simple physical process. To transfer energy to something, you do work on it. And remember, to do work on any object, you have to push on it, so the force has to be there, and it has to move a distance in the direction of your force. So you can do work on a ball. It's a lot harder to do work on a table because the table won't move for all practical purposes. So I can push on the table, but I can't, or down, pick a direction that makes more sense. I can't do work on the table because it won't move a distance in the direction of my force. I can easily do work on a ball. Questions about work, lingering ideas, issues with that? So you can watch, I can put energy into the ball by pushing it and having it move a distance in the direction of my force. It then has more energy than it had before. In this case, it's more gravitational potential energy than it had before. In this case, it's more kinetic energy than it had before. It's a pretty dead ball, is that true? Yes. Not, yeah. Okay. An aside about energy. Energy has no direction to it. It is just an amount. You have 10 units of energy. The standard unit, the SI or metric system unit of energy is the joule, exactly the same as a Newton meter. And it has no direction, not left, right, none of that. Just an amount. And it can have different forms. There's the energy of motion, that's so-called kinetic energy, these various potential energies, which is energy. Oh, thanks, Al. It bounces, woo! Nothing like having a little air in it. The next topic after spring scales is bouncing balls, so we'll know all about this shortly. Thermal energy is just sliced up little teeny pieces of kinetic and potential energies. The individual pieces, none of them are conserved by themselves. So kinetic energy is not a conserved quantity because that's just part of the overall conserved quantity. The conserved quantity is energy. The pieces aren't conserved. So you can turn, for example, this is full of gravitational potential energy. As it descended, it was turning its gravitational potential energy into kinetic. So the kinetic was going up. The overall kinetic energy of the universe was increasing. The overall gravitational potential energy of the universe was decreasing. They swapped. Individually then, they are not conserved quantities. The sum, that is energy, is the conserved quantity. Is that okay with people? Or questions about that idea? All right. So energy, you can carry it with you. You transfer it by doing work. Things have to move in order for work to be done. So the transfer of energy involves motion. It also involves forces. Momentum, a different conserved quantity, totally about motion. So unlike energy, momentum has a direction. The direction matters. This is momentum to the right. It's completely different. My momentum changed dramatically in going from rightward to leftward. In fact, this is rightward momentum. You could talk about this as leftward momentum, or equivalently, a negative amount of rightward momentum. They're just the same thing. So it's a big change, even though I'm traveling at the same speed in the two versions. Questions about what momentum looks like? And I talked about not being able to hide it. There's no thermal momentum where you chop it up in little bits and sort of hide it in the material. It's now hot. No, momentum is all about movement. If an object's got momentum to the right, you're going to see it move. You may mask it temporarily by hiding it in a box, but it's going to work its way across the box and come out the side. So you can't make it disappear temporarily, well, more than very, very temporarily. To transfer momentum, you have to, because it's a conserved quantity, you move it around. And the way you move it is by way of impulses, which involve pushing on something, not for distance, as in the transfer of energy, but for time. And so if I push on the table, for example, downward, I am transferring downward momentum into the table. Now you don't see it happen because the table is transferring the downward momentum into the floor, which is transferring it into the earth, and never accumulates. But if I push leftward on the ball, which no longer has anything to give it to, basically, I give it leftward momentum by pushing it leftward for time, and it gave leftward momentum to the other ball when it hit and pushed leftward for time on the other ball. So momentum moves around by way of these impulses, force times time. Questions about that, those transfers? I went on at great length about, in each of these transfers, since it's one quantity times another, it's force times something else, you can use a big force for a little something else, or a little force for a big something else. So big force, little time can be the same transfer of momentum as little force for big time. And this has consequences, like it's not fun to use your body to transfer momentum or energy in small distances or short times, because that involves big forces and they hurt. Okay? The last one, just to finish out with this, angular momentum is another conserved quantity that you carry with you, and you transfer it by way of angular impulses. You exert twists on things for time. So for me to give angular momentum to the ball, I twist it for time, it's got it, and then I took it back out. So while it was in the air, which I'll come back to in a second, it had trapped in it a certain amount of angular momentum, and it couldn't stop spinning until it gave it back to me by a reverse twist, the opposite twist. All right, that one too? One tidbit about this, while it's in the air, this is a homework problem from the bowling story. While it's in the air, what about it is constant? It's certainly not its speed, because the ball is going from traveling fast up to stopped, almost motionless at the top, to fast down. So its speed is going all over the place. So is its velocity, because after all, it's accelerating downward. It's a falling object. So a falling object has a downward acceleration, the famous acceleration due to gravity, and so its velocity is just evolving the whole time. It's never constant. All right? So speed, velocity, they're right out of the possibilities. Yeah?
So velocity is speed in a direction, right?
Velocity is a speed and a direction.
So, and the question was assuming no air resistance.
Yes?
So assume that no x velocity would be lost. And if you're measuring on this axis,
Yeah.
the velocity would be constant, right?
So the question is along this axis, the horizontal axis of an object moving, the velocity is constant. That's actually what would be called the component of velocity along the horizontal axis. The ball only has one velocity. It is its motion, how fast it's traveling, and its direction of travel in all directions, all taken into account. So this ball, like that, started off with a velocity that consisted of a speed. It was traveling at a certain speed, and it was heading in this direction, which had a component. So now we're getting into the details of how physicists actually tackle these problems. This has a component in the vertical direction, which is sort of the portion of overall velocity that was heading straight up, and it also has a horizontal component. Velocities, and it is true that the horizontal component of velocity is constant. So had I included in that list of possibilities, this was for a bowling pin, the horizontal component of velocity of the bowling pin, that would be constant. You're right. It's coasting horizontally, assuming no air resistance, as you said. Is that okay with everybody? But if we use overall velocity and overall speed, they are neither of them constant, because the thing is, it's a falling object. Its velocity is changing. It is possible for something to undergo a change in velocity without undergoing a change in speed, but it's a special case. It's when something's traveling in a circle. It can go its constant speed, always changing its direction of travel. So we'll talk about that. A carousel, when you're riding a carousel at the state fair or whatever, you're actually going steadily in speed, but always changing your direction of travel. All right? Neglecting that one special case, which is not relevant for a falling object, its speed changes as it falls. How about momentum? Momentum, there are two ways of looking at why momentum is not constant for any object that's falling. One is that momentum is the product, its momentum is the product of its mass times its velocity. That's an observation about how you actually measure the momentum of an object. And since its velocity is changing with time, surely its momentum is changing with time as well. The more sophisticated way of looking at this question, though, is to observe that when the ball's in the air, it's experiencing only one force, gravity down. If there's only one force acting on it, which is gravity downward, gravity is doing an impulse on the ball. It's pouring downward momentum into the ball. So the ball is accumulating more and more downward momentum, and it's certainly not constant. Is that okay? By process of elimination for that question, it left angular momentum as a possibility. And that's where why am I doing this? The angular momentum of an object that is neglecting air, that is above the ground, the angular momentum is constant about its own natural pivot, that is about its center of mass. So this ball, when it's in the air, and I say it's in the air, but I really want the air to be gone because the air is a nuisance. It's going to cause trouble. But neglecting the air's effects, it's got constant angular momentum about its own natural pivot, its own center of mass. And why is that? First off, angular momentum is a conserved quantity. So if it's going to be changing, it had better be exchanging with something else. So something will have to be exerting a twist on it for time. That's how angular momentum is transferred. Angular impulse, a twist, a torque for time. Well, when it's not touching anything, the only thing acting on it is gravity. So gravity is certainly exerting a force on it and changing its momentum. Is gravity exerting a torque on it and thereby changing its angular momentum? And the answer is no. And why not? Because if you think about where gravity effectively acts, I've mentioned from time to time in class that an object's weight is effectively located at the center of gravity of the object. That's the point at which you can approximate, or simplify. It's not an approximation, it's a simplification. The gravity effectively acts at that point. And that, for basketball, it's pretty much dead center in the middle of the basketball where I can't touch it and point it out to you, but it's in there. So that's where gravity is yanking. That happens to coincide with the basketball's center of mass, its natural pivot. They share the same point in space, even though they're different concepts. One's a weight, one's a mass. And the result is gravity is yanking right at the pivot. And I've told you, like in the context of the seesaws, you can't produce a torque on a seesaw or a door or whatever by pushing at the pivot. It has no lever arm to work with. You can't twist it. So pushing at the hinges of the door doesn't open or close the door. Pushing at the pivot of the seesaw doesn't make the seesaw begin to rock one way or the other. And the same thing, when gravity yanks at the center of gravity of an object, it doesn't produce any torque. And okay, with a bowling pin, you don't care so much, but if this is you, if you're a gymnast, if you're diving off a diving board, pick any context in which you are a falling object, you have trapped in you a certain amount of angular momentum that you received or acquired during the process of leaving behind all the objects you were on, the diving board, for example. You've got angular momentum. You can't change it. It's stuck in you. You can't exchange it with the earth. Air, maybe, but the air is pretty fluffy stuff, so you're not going to get much action out of it. So a diver leaving the diving board and wanting to do somersaults or various complicated twists and spins has to leave the diving board with all that angular momentum on board and use it strategically to do the flips and spins that he or she wants to do. Nobody can jump off the diving board perfectly upright, like off we go, and then start to spin, and then come out totally straight and descend the next 10 feet exactly vertical the whole time. You can't do it. That violates conservation of angular momentum. And so if you watch people dive, you will see how carefully they use the angular momentum they've got. If they want to rotate faster, they use the skater trick. They pull into a tight tuck of some sort so that they go from rotating slowly when they have a large rotational mass because they're extended outward. Lots of their mass is far from their natural pivot, their center of mass. They pull into it some tight structure so that their rotational mass is much smaller. Whatever angular momentum they have now causes them to rotate much faster so that their angular momentum is constant. Their rotational mass goes down, then their angular velocity has to go up. And at the last moment, when they want to enter the water and look as though they're just slicing into it absolutely vertically the whole time, they can't actually become motionless rotationally. They're still rotating, but they can open up so that they have a large rotational mass, and therefore their angular velocity plummets to compensate. Questions? Yeah. Yeah. So if an object had its center of gravity at a different location from its center of mass, could gravity influence its rotation? And the answer is yes. And what that brings up is, in what circumstance would gravity, the center of gravity, be different from the center of mass? And there is one. I mean, there's a very straightforward one. The moon. The moon is so far from the Earth, and it's so big that it's not that far from the Earth. It's so big that gravity, I told you at some point along the way, that gravity isn't actually constant. It does vary with distance from the center of the Earth. It varies with distance in general. And so the moon, being farther from the Earth than we are, experiences a weaker gravity due to the Earth. So far, so good? It is falling. It's a falling object. It is falling toward the Earth. It's in free fall. There's no air up there, so it's super duper good free fall. The difference is it's so far away that its acceleration due to gravity is dinky. I could know it off the top of my head, but I don't. It's down to centimeters per second squared, something like that. But the moon's big. And so the near side of the moon experiences slightly stronger gravity, being closer to the Earth, than the far side of the moon. As a result, the moon's weight due to the Earth is a little closer to us because of the stronger gravity close to us than the center of mass of the moon. Can you visualize that? Its center of gravity is actually pulled toward the Earth because the gravity is stronger on our side of the moon. So there is a possibility now for the Earth to twist the moon about its own natural pivot, because it's pulling on this closer portion of the moon than the moon's natural pivot. And to oversimplify a lot of things, this is why the moon has over time become locked such that we always see the same face of the moon. You've looked up at the moon, you've seen the same craters your whole life. You've never seen the back side of the moon. It's not visible from Earth. It was never seen before until they sent spacecraft around to the back of the moon. Because the moon orbits us like this. You know, I'm looking at Rawlings here. This is not a product placement, it's an accident. Okay, we always see Rawlings. Because the moon, which could have been spinning independently, has lost its ability to spin over the millennia, geological time. It's now always facing the same part towards us. And that came about in part because of the displacement of the center of gravity from the center of mass. Is that okay? Any other questions about these three conserved quantities? All right. So spring scales, let me get on to business, get the spring scale story done. Spring scales, it turns out, are virtually any scale you ever encounter, including electronic scales that you see at grocery stores or you have yourself. Yeah. Okay, so a question leading up to, to jump into the middle of the issues are a diver on a springboard. So a springboard, the name spring should bring to mind. It's got to do with a spring. And when you go out on a springboard as a diver, the springboard bends. I don't know whether you've ever done it, but here's the springboard, and out you walk out there, and it's no longer as high as it was before you stood on it. So here it is without anybody on it. And it's got some bouncing motion, which is interesting and important. But you go out there, there you are. Okay, oh boy, we're high above the water. I'm not going to do this. Okay, all right. Sorry, you have to. Right, peer pressure. Okay, I'll do it. You stand out here, and it bounces for a little while. You let it settle down. Well, if you let it settle down and you're standing on it, you discover it has descended a certain distance relative to where it was when no one was on it. So now if a second person joins you, so instead of just one of you out there, it's two of you out there. The board descends again with two of you, as opposed, it descended a certain distance with one of you, it descended a certain other distance with two of you. Compare those two distances. Is it bending the same as it did with just you? Is it bending twice as far as with just you? Or 4 times as far as with just you? So this question, wording these versions of this question is difficult. The problem set has a different wording. Read the wording carefully. The first problem, you can read it differently, and it has a specific meaning. Okay, so how many think that it's going to bend the same distance with 2 people on it as it did with 1 person on it? How many people think B, that it's going to be twice as far as with 1 person on it? Okay, how about 4 times as far? Okay, there are a few votes for 4 times as far. Nobody's going for the same. Twice. It is twice. And what this is observing is that springy things, simple springs, and the world is full of simple springs, and I'll pin down what that means. They have this characteristic to an excellent approximation. I mean, it's not perfect, but it's very close, that if you disturb them away from their favorite shape or position, you disturb them away from it, they fight to go back with they develop a force on their own end that wants to push them back. And that force is proportional to how far you've taken them away from where they want to be. So a classic spring, this guy's a classic spring, so you can see it, but it's so stiff I'm not sure I can make much movement out of it. Yeah, it's kind of hopeless. This guy, you can you see this guy? Enough that, I mean, this is show and tell, so it doesn't make a whole lot of difference. If this is its favorite arrangement, it loves to be just sort of like this, in every way, including like bent. It doesn't want to be bent. If I stretch it 1 unit away from its favorite length, it's now longer than it wants to be, it will fight to go back. And it will develop forces on its own ends that are proportional to how far I take it away from its favorite shape and everything else. So the more I stretch it, the more it pulls back. And you've seen this, if not sort of quantifying it, you know that the farther you bend something away from its favorite shape, whether this is a springboard now, the farther I bend it away from its favorite shape, being that one, the more it pushes back up to a point. Of course, this one, if I take it far enough, it will break, and we could do that, but then Al would be unhappy with me, so I won't do it. So I can take it 1 unit away from favorite, we get 1 unit of force, say. 2 units away from favorite, 2 units of force. 3 units away, 3 units of force, and everything like that. Is that okay, or questions about that idea? This applies to a huge variety of spring-like things, simple springs. And simple springs, just to sort of give you some sense of what to consider fitting the mold, things that have sort of one important dimension to them. They operate essentially along some straight line. This guy obviously has an important dimension, this one, along its length. It's a one-dimensional object. It's as opposed to what? As opposed to a ball. The ball's behavior is not spring-like. But a straight line thing like a stick, if you bend it away from straight, it develops this what's called a restoring force, the force back towards its favorite shape. It's proportional to how far you took it away from its favorite shape. The same with a spring, a conventional spring. Okay, it's got obviously one dimension that's important. Its length, along its length. What other possibilities are there? Nothing else that comes to mind right here. With a ball surface, it's not one-dimensional anymore because it's got action going in at least 2 dimensions. If I push the surface in, it's not uniform along one dimension. It's got this curvature to it. It's strange, and it's got a strange relationship, a more complicated relationship between how far you push it in and how hard it pushes back. This won't be spring-like. These one-dimensional things will be. If that doesn't make sense, it's not going to be terribly important, but I say it anyway. Okay, so some observations about spring scales. Not surprising, spring scales are going to be built about spring-like things like I've just showed you. Sticks or coils or those sorts of structures that are one-dimensional. They move downward during weighing, and if you don't believe that, here's a old clunky grocery scale, and if I want to weigh this block, in addition to having the dial move, the platform moves. I don't know whether you can see that descent. We can do this. What are my chances of remembering to undo it? Okay, there you are. You can see the scale. All right? Pay attention to the height of this platform. It's going up. See it up? It's up, and now when it's weighing something, it actually descended by about 1 centimeter. I'm going to unweigh it. And you can see that this cutoff dial here becomes more visible as the platform goes up. So just as a general observation, when you put stuff on a scale, I remembered. Whew, whiplash. When you put stuff on a scale, the scale actually descends. It's doing the negotiation I talked about when we put the wagon on the sidewalk. That's all going on. And it negotiates and settles. So that's one observation. It takes some time to settle because the negotiation is going on. It's trying to figure out how hard should I push up, which is related to how far should my spring bend. And last thing here is the scales are only accurate when everything is at rest. You all live in an era where all scales are electronic, or virtually all of them. I grew up in an era where the bathroom scales were all dial scales. Do any of you have one of these things kicking around the house still? All right. So as a kid, back in the day when I weighed 30 pounds or 40 pounds, you'd get on the scale, and I knew that it could go as high as 300 pounds. They all, at least in that era, did that. Could you actually make it read almost 300? And you could. You get on, you jump up and down, woo! Okay? You can make it read all over the place, and it would read 300 shortly before it broke. And what you learn from that, other than don't. Okay. These painful lessons about what not to do with expensive toys, is the scale is genuinely trying to report your weight, but the weighing process itself requires that you be not accelerating. And if you're accelerating up and down by jumping up and down on the scale, what it reports as your weight isn't your weight. It's related, but it's not your weight. And so that's something I got to deal with too. All right? So the questions to go through. Basically, what are you weighing? Or what are you measuring, I should say? And finally, ultimately, follow the path towards how the scale does the measurement. Okay, so the first one is what is a scale weighing? Measuring. It measures weight. One way you would know this is by imagining taking a spring scale like this, or any of these scales, out into deep space where there is no gravity. Imagine putting some groceries on a big watermelon. You plop it on top of the scale. Well, if there's no gravity around, the scale's going to read 0. It just doesn't matter what you put on it. The issue is there is nothing pulling down on the watermelon anymore because there's no gravity, so the scale doesn't have to push up on the watermelon to support it. So scales read 0. So scales typically report the weight of an object, and that's a perfectly reasonable thing to report. But there are some issues then. Objects have both mass and weight. So this sort of rehash the story I've talked about before, but an object's mass and weight are proportional to one another if you do the comparison at a known location. You stay there. You're always there. Here on the surface of the Earth, ideally right here in the front of room 203 of the physics building. If you go somewhere else, the weight and mass are still proportional to each other, but the proportionality has changed because the acceleration due to gravity is a little bit location dependent. An object's mass is really it's the gold standard for quantifying how much of the object is there. So if you want to buy a watermelon, you want to be absolutely confident you know exactly what's present in that watermelon, buy it by mass. It's 2.5 kilograms exactly. And now you really know how much is there. You can go anywhere in the universe, and it's going to still have 2.5 pounds of mass. Because mass has nothing to do with gravity. It's an inertial thing. It's how hard is it to make that watermelon accelerate to the right or accelerate to the left. It's the measure of the object's inertia. Okay? Weight is how hard the local gravity pulls down on the watermelon. And that might be, remember, it's measured in units of force now, not units of mass. So it's not in kilograms, it's in newtons. Or if you want to think English, or, well, American, it's pounds. Okay, so when you buy something by pounds, I'm a little oversimplifying, but you're measuring it by weight, and if you went to a place where gravity was stronger, it would weigh more. So there's a little bit of flakiness here. I mean, this is probably fine for watermelons. If you're going to go buying gold, you probably do care about the slight variations in local gravity. If you're going to go buy 1 pound of gold, go to the place where gravity is the weakest, because they're going to have to put the most gold molecules on the scale to crank it all the way up to read 1 pound. So that would be, go to the equator. They'll actually have to put more gold on the scale to have it read 1 pound, because gravity's weak there. All right? Little odds and ends then about mass as a measure versus weight as a measure. Mass really beautifully characterizes how much of something there is. 1 kilogram of gold in principle has a certain number of gold atoms, and that should be the same anywhere in the universe. It's really totally quantifies the substance. In fact, well, there are long stories to say about mass and trying to define the kilogram, but I'll leave that. In principle, you can measure mass perfectly with a simple process. You exert a 1 Newton force on the object, and you see what its acceleration is, and you measure the acceleration, and you divide F equals ma, right? M equals F over A. You divide the force by the acceleration, and you get the mass. Did I do that right? F equals ma. F over A equals m, yeah. Okay? So you can get it exactly. The problem is it's really hard to pull off. It's really hard to exert a 1 Newton force on something that you know is really, really, really 1 Newton. Get gravity out of the story. You do it yourself, and then measure its acceleration really carefully, really hard. All these are too hard measurements. So it's rarely done. I did mention at one point that astronauts were quantified in this manner. They would exert known forces on them and see what their acceleration was. Usually they would do it by shaking, not just one direction. You'd actually rhythmically take them back and forth and see how much acceleration you got out of them for a rhythmic force back and forth. But this is not how in a grocery store is not going to operate this way. So instead, they measure weight. How do you measure weight? Well, first of all, it's a little problematic because it depends on location. So wherever you install a scale, a spring scale, you have to then do what's called calibrate it. You have to make accommodations for the location and therefore the variation in gravity. So once you install it, you take some known objects that you know what their mass is and therefore what their weight would be at an official location, and you then compare that with what the weight is here, and you make adjustments then so that when this scale reports weight, it's reporting something that's somehow standardized so that everybody knows that you're getting the right amount of watermelon or maybe gold. So you're okay with the idea that weight is a little flaky because of the strength of gravity is involved? The niceness of measuring weight is that you can do it pretty easily. The way spring scales work, so cut to the chase, the way a spring scale works, given that this thing weighs, I don't know, about 60 newtons, that's how hard gravity is pulling on because my hand's calibrated. No, not really, because I've put it on the scale before. For you guys, is that true or did I weigh the bowling ball? I don't know. I have no idea what this thing weighs. 49 newtons. It's telling us what it weighs, and how does it know? The way it knows is it is supporting that weight, that object, the block. It's supporting that object's weight. So the object has a weight down. How hard is the scale pushing up on that block? Tell me how hard it's pushing up. It's an upward force, obviously, right? It's equal in amount to the block's weight. You know, I mean, yeah, this is hard to do. Everybody respond, right? They show that in television sometimes. Everybody choreographed answers like, are you kidding? Is this reality TV? Well, it is reality TV, but reality TV is not reality. Okay, so what the scale is doing then is it's perfectly supporting the block's weight. And it is then telling you how hard, the scale is telling you how hard the scale is pushing up on whatever's above it. It doesn't care whether it's supporting weight or anything. It just says, I'm pushing up with 49 newtons of force. If that happens to be some object sitting on me, well, fine. So measuring weight turns out to be fairly simple because it's pretty easy to make a gadget that will tell you how hard it is pushing on something. How do you do that? Use a spring. And why is there a connection between how hard the scale pushes up on something and this block's weight? It's because those two forces, the block's weight downward and the scale's force upward, sum to zero. And how do we know they sum to zero right now? What's the block not doing? It's not accelerating. It's motionless and staying motionless. So we know those two forces cancel, and therefore the weight down and the scale's push up are equal in amount. So that's all we need to know. If they don't cancel, they will be different in value, and what the scale then reads may be not very closely related to the block's weight. And that would happen when the block is accelerating. So while the block is accelerating, the two forces don't match. The weight down and the scale's force up, they're different. Okay, the consequence on that for the block is the block accelerates. The consequence for you, the checkout person at the grocery store, is don't take the scale's reported value and say that's the weight of the watermelon. They're not the same because the watermelon's accelerating. All right? I am walking, I'm drilling through my slides in a different order, but that's okay. So the way in which a spring scale measures weight, it takes advantage of this situation, that when the block is not accelerating, which is to say when it's at net force zero and therefore is at equilibrium. It's mechanical equilibrium. I've used that word back in the days of talking about the wagon sitting on the sidewalk. Equilibrium means zero net force and therefore not accelerating. So when the block is at equilibrium, the weight down and the scale's force up sum to zero. And if you can coax the spring scale to tell you how hard it's pushing up, you know what the weight of the block is then. Everybody okay with a logical sequence of, well, tonight, or as soon as you can pull yourself to do it, kick yourself to do it, think through that the scale isn't literally reporting the block's weight. It's reporting how hard it's pushing up on the block. And if the block is at equilibrium and not accelerating, that's good enough. How hard the scale is pushing up on the block gives you all the information you need to know, because it's going to be equal in amount to the weight of the block in the opposite direction. All right, so that's what it's doing. The scale is supporting the block's weight at equilibrium and telling you how hard it's pushing to do that. So why the spring? Because springs have this great behavior. This is more of that same story. Springs have this nice behavior that if you look at them when they're experiencing no deformation, when they're at their favorite shape, which I call or equilibrium shape. This spring right now is at its equilibrium shape. The I'll leave balls alone. This stick is at its equilibrium shape. It's at the shape at which all its pieces are experiencing zero net force. It's happy, 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 no accelerations. If you look at that as the starting point and you deform it, you take it away from its equilibrium shape, pretty much in any direction, it will develop forces that try to pull its pieces back to the equilibrium. And those restoring forces, they're called restoring because they restore towards equilibrium, they are proportional to how far you've taken it away from equilibrium. And I did this before, right? This is equilibrium shape in all respects. You take it away from equilibrium, and you go one bit of distance, you get 1 bit of restoring force. Two bits of distance, you get 2 bits of restoring force, and so on. Same with stretchy springs, compression springs. It's remarkably close to perfect. And I can show you that up here. This behavior is actually known as Hooke's law. There it is, Hooke's law. It's in the yellow there. It's just observing that the restoring force, that is the internal force that the spring exerts on its own end, is equal to minus a spring constant. The spring constant characterizes the stiffness of the spring. The bigger the spring constant, the more stiff it is, the madder it gets when you distort it. The minus sign says that the force that comes up points back towards equilibrium. And the other piece here is just the distortion, how far you distort it. So that equation shouldn't be, you don't remember it as an equation, remember it as a concept. That when you distort something, it fights to go back, and the fight is proportional to how far you take it out of, how far you take it away from equilibrium. So now we're looking at, there's a spring up here, which is out of view at this point, but this structure here with the pointers is hanging on the spring. And gravity does appear to be involved in this story right now, but it turns out that gravity, this would be true with or without gravity. If you exert a known force on the spring, you'll stretch it a known distance. Okay, don't worry about my harangue about gravity. This is where the spring is when it's not supporting any weight. If I make it support 1 unit of weight, it bounces for a while, which is interesting, and we'll come back to it, though not today, so that my choice of having the problem set due on Friday was prescient, a word I rarely use, but okay, I used it. You can see we stretched the spring. The spring needed to get longer in order to summon up enough restoring force to support that, actually it's a 50-gram disc. So I can mark where that guy is. Of course, not from behind because I can't see what's going on. All right, so there's the stretch that occurs when it's supporting 50 grams. And if I add a second 50-gram weight, it bounces again, and when it settles down, it has stretched another bit of distance, and the distances are the same. Okay, there. You know, with each additional 50-gram object hanging on there and adding its weight, it's going to stretch another this much. So if we can get, so basically we've made everything we need for a spring scale, except we need to put labels on here that say that if it's here, it's supporting, I'm probably right in the way, yeah? If you can't see what's on this, what's actually located on this hanging widget, but the widget is here, you know it's supporting no weight. If it's here, you know it's supporting 1 disc's worth of weight. If it's here, you know it's supporting 2 discs worth of weight. If it's here, it's 1.5 unit disc worth. So if we did it, if we made this 0, and if this were 1 pound and 2 pounds, we could measure weight by where the thing settles down. And that's the story, except for some of the details and the bouncing process. And those, they'll wait until Wednesday.